Welcome to the next lecture on operating systems. In today's lecture, we will learn about process concepts, process scheduling, operations on processes, inter-process communication, and with respect to inter-process communication, we will learn about two models, that is shared memory systems and message passing systems. So an operating system executes a variety of programs that run as a process. So what is a process? Simply, a process is a program in execution. Process execution must progress in sequential fashion, no parallel execution of instructions of a single process. So if it is a single processor system, uniprocessor system, we need to make in our mind that only one instruction can be executed at any time. The process has multiple portions or parts. The program code, also called text section, current activity including program counter, stack, data section, and heap for containing memory dynamically allocated during the runtime. Program is a passive entity stored on a disk. It is a executable file, but process is active. So once the program gets the attention of CPU, then it becomes a process. It is active. Program becomes process when an executable file is loaded into the memory. So execution of programs started via GUI mouse clicks command line entry of its name. So simply double clicking a particular word processor, a particular file, everything considered as a process. So if you see here, so there is a text section, data section, heap section, stack section, and this is the exact code of the corresponding process. So here see memory layout of a C program. So if it's a typical example, so there is argument, right? This is a stack heap, uninitialized data, initialized data, and the text section, right? So int x it does not have any value, so it is not initialized, so it is uninitialized data. It will be stored in uninitialized data. Y is equal to 15. It is initialized with a value. It is stored in initialized data, right? So the argument section is stored in the here in this, and if you see here the values, these are all stack. It is stored in the stack section, right? So this is how a particular memory layout of a particular program that is available. Right? As a process executes, it may change its state. So there are typically 5 states for a process. If it is a new, that is new state means the process is being created. Running state, instructions are being executed. Waiting state, the process is waiting for some event to occur. Ready state, the process is waiting to be assigned to a processor. Terminated, the process has finished execution. So this is the state schematic of process. So new state means the process is newly admitted and it is ready for execution. It is in the ready state. Whenever a process is in set of processes in ready state, they may get the attention of CPU. So when they get the attention of CPU, this transition takes place. It moves from ready to running state. In the running state, there can be 3 events that can occur. Either the process is completed successfully and exits the system, so it is go to the terminated state, or an interrupt may occur. So because of that interrupt, the corresponding process is temporarily stopped executing and it is pushed to the ready state. Or the third scenario during the running state, that is the process needs to wait for an IO event. So because of that, it is pushed on to the waiting state, and from the waiting state, if the IO is completed or the event is completed, the process can be moved to the ready state. So this is the typical process states and its transitions. Every process will be associated with a process control block. It is also called as task control block. It is a data structure. This data structure contains the entire information associated with each process, like process state, which state the process is, program counter, CPU registers, CPU scheduling information, memory management information, accounting information, and IO status information. These are all the typical parameters or the corresponding information that is available to each processes, so each and every information about the processes are available in the process control block. Process scheduling. So whenever there are n number of processes in the ready, okay, so their scheduling mechanism should be implemented for getting the attention of CPU. That is which process may enter getting the attention of CPU. So the process scheduler selects the among available processes for next execution on CPU core. Now what is the goal of the scheduler should be? The goal of the scheduler should be maximize the CPU utilization. Okay, so as quickly as possible the processor or CPU should switch from the one process to the next process, so that the corresponding execution throughput is increased. Throughput is maximum number of instructions executed per unit of time. Now for scheduler, okay, to select among the n number of processes that is waiting in the ready queue, there is different types of queues employed. Scheduling queues. So the scheduling queues are normally ready queue and wait queue. Ready queue is set of all processes residing in main memory ready and waiting to execute. Wait queue, set of processes waiting for an event. So the ready and wait queues can be implemented using the linked list concept like this. The representation of the process scheduling. So the ready queue, so the process is entered into the ready queue and it is getting the attention of CPU. During the course of execution it may wait for IO, so it is moved to the IO request queue, and once the IO is completed then it is moved to the ready queue. Running process may exhaust its time. Okay, so for example, if it is a round robin scheduling that is implemented, each and every process will be have a certain time quantum allocated, 3 millisecond, 4 millisecond, like that. So if the time quantum is expired, then it will get out of the attention of CPU and it will be waiting in the ready queue, pushed onto the ready queue for the next chance. Or the child process, currently executing processes, child process will be created. The corresponding parent process will be pushed onto the ready queue until the child is terminated. So that is another scenario. And during the course of execution, an interrupt may occur. Because of the interrupt, the process that currently executed is temporarily suspended and the interrupt is serviced. Until the interrupt completes, the corresponding process is pushed onto the ready queue. So these are all the representation of process scheduling mechanism and the process movement from one queue to the another queue. See here, the context switch occurs when the CPU switches from one process to the other. So this is typical scenario what happens when the context switch occurs. The process P0 is currently executing. The operating system is interrupt driven. So an interrupt occurs. Now what happens? The operating system saves the state of the corresponding execution P0 into the PCP0. So what the current status of P0 is saved into the PCP0. Now the process switch over to the next process, right? So that is we will consider as P1. Now the state of P1 should be reloaded into the memory from PCP1. Okay, every process will be associated the process control block. So there will be a process control block for P1 also. The state of that thing should be loaded from the PCB1 to the memory. Now the process P1 is executing and again the interrupt occurs. So the interrupt occurs means the current state of PCB1 is saved and the processor CPU moves to the next process P0, reloading the state from the PCP0. In this way, one process switching from one process to the next process occurs through the context switch. So whenever the context switch happens, saving the state of the current process, reloading the state of the next process to be executed is done. So if you see here, all these should be done with minimal time so that the corresponding user program is not delayed and the performance is not degraded. So when CPU switches to another process, the system must save the state of the old process and load the saved state from the new process through a context switch. Context of a process represented in the PCB. Context switch time is purely overhead. It is a overhead. The system does no useful work while switching. So while the switching takes place, the no useful is done. So it is a overhead to the system. Right? The more complex the operating system and the process control block, the longer the context switch. So that should be taken care. Operations on processes. System must provide mechanisms for process creation, process termination. So a parent process creates a child processes, which in turn creates other processes, forming a tree of processes. So generally, process identified and managed through a process identifier, which is PID. Resource sharing options. Parent and children share all resources. Children share subset of parent resources. Parent and child share no resources. These are all the three different options of resource sharing between the parent and child processes. Execution options. Parent and children execute concurrently. Parent waits until child terminates. These two scenarios are options available during the course of execution. Address space. Child can duplicate of parent. Child has a program loaded into it. Child can be duplicates or it has its own program. So in Unix example, fork system is used for creating a process. Fork system call. So this exe is another system call used after the fork to replace the process. Okay, to replace the process's memory space with a new program. So parent process calls wait system call for child to terminate. So this is the typical execution scenario of parent and child process. So whenever we need to create a process, we use fork system call. Whenever the corresponding replacing the process's memory space with the new program, we need to use exe system call after a fork. So this is the typical example program for creating a process using fork system call. So PID is equal to fork. If it is successful, there will be a 0. PID value will be 0. So if it is less than 0, then we can conclude that an error has occurred during the execution of fork system call. Okay. So that if PID equal to 0, the child process is created. Okay, else the parent will wait for until the child is completed. So this is the typical program for creating a process. Process termination. Process executes last statement and then asks the operating system to delete it using the exit system call. Okay, the parent may terminate the execution of children processes using the abort system call. Why? Child has exceeded the allocated resources. So it is forcefully stopping the execution of child using abort system call because the child has executed allocated resources. Task assigned to child is no longer required, or the parent is exiting. Parent itself exiting so that the child has no usefulness. So the operating system does not allow a child to continue if its parent terminates. So some operating system do not allow child to exist if its parent has terminated. If a process terminates, then all the children must be terminated. This condition is called as cascading termination. All children, grandchildren, etc. are terminated. The termination is initiated by the operating system. The parent process may wait for termination of a child process by using the wait system call. The call returns the status information and the PID of the terminated process. If no parent waiting, process is a zombie. If parent terminated without invoking wait, then process is an orphan. Now coming to the inter-process communication. So processes within a system may be independent or cooperating. So the cooperating processes can affect or be affected by other processes, including sharing data. Because the cooperating processes may share data, so we need an inter-process communication mechanism for these cooperating processes. So what are all the reasons for cooperating processes? There may be need for information sharing between the processes, for computation speed up, modularity and convenience. So cooperating processes needs inter-process communication facility. So this inter-process communication facility is provided through set of APIs, okay, by the operating system. So two general models of IPC is implemented, that is called a shared memory and message passing. So here see, this is the shared memory. So if process A and process B needs to communicate, okay, the kernel provides a shared memory region for these two processes. So any type of data should be shared, will be kept into the shared memory and each process can communicate by sharing this memory. Message passing. Message passing is implemented through a set of message queue between set of processes need to communicate, and this is initiated through a mailbox. Okay, so a process may keep the message in the queue and the next process may take the message from the queue. So this is how the message passing model is implemented for inter-process communication. So with a typical example we can understand the corresponding why we need inter-process communication facility. The typical example is a producer-consumer problem. The producer is an entity which produces a particular data. Consumer process is that using the data produced by the producer process. Okay, so producer produces information that is consumed by a consumer process. Here there are two variations. Either this can be implemented using unbounded buffer, where there is no places no practical limit on the size of the buffer. Producer never waits. Producer continuously produces because there is no limit in the buffer. Storage. Right. Consumer waits if there is no buffer to consume. So this is the case of unbounded buffer. Bounded buffer. Okay, there is a fixed size buffer size storage. The producer should wait if all the buffers are full. Similarly, the consumer should wait if there is no buffer to consume. Right? IPC, shared memory model. So in area of memory shared among all the processes that wish to communicate. The communication is under the control of that user processes, not the operating system. Major issue to provide mechanism that allow the user processes to synchronize their actions when they access shared memory. Right? So this is the typical pseudocode for bounded buffer shared memory solution. So this is that buffer we are going to share among the processor, that is producer process, and the consumer process. We are going to implement this in and out pointer initialized to 0, right, for keep tracking of the buffer size. So this solution which we are going to provide is only can use buffer size -1 elements. So this is the producer process. So while in plus 1 mod buffer size is equal to out, this means this condition means the buffer is full. The producer cannot produce the next item. Okay. Similarly, this is the consumer process. The consumer process will wait when in is equal to out, when in pointer is equal to out pointer, when both in and out point to the same location, when then the buffer is empty. Right. So if we need to use all the buffer locations, so what is the kind of change we can do? We can implement using a counter. Okay, this counter variable is initialized to 0. It is incremented by the producer after it produces a new buffer. The integer counter is decremented by the consumer after it consumes a buffer. So here that is a modification of the code. The producer process, we are going to use a counter which is incremented after producing an item. The consumer process decrements this counter when any particular item is consumed. Okay, so here a race condition may occur. What is this race condition? We will look up this example. This counter plus plus post increment counter plus plus, okay, this single line statement in C is interleaved, or it is going to have these three set of statements when it is implemented. So as we have learned previously, if any data should be processed or manipulated, it should reside in the register. It comes to the register of the processor, right? So a register 1 is assigned the counter value, register 1 is incremented, and then the counter is reassigned with the value of register. So these three statements, okay, this one counter plus plus is implemented in three sets of statements. Similarly, the counter minus minus decrement operator is also implemented using these three sets of statements. Now during the course of execution, interleaved execution of these producer process and consumer process may occur like this. So if you see, producer executes the first statement, register 1 is equal to counter. Now initially we consider the count value as 5, so register 1 is equal to 5. Now the producer process is executing next time interval, register 1 is equal to register 1 plus 1. Now the register 1 becomes 6. Now, because of the interleaved execution of both the producer and the consumer process, let us consider that consumer executes now and it assigns the value of counter to the register 2. Now the register 2 is having the value 5. Okay, it has not updated with the 6 because of this interleaved execution, because the counter value has not been complete. These three sets of statements is not completely executed. Right now, consumer executes the next statement, register 2 equal to register 2 minus 1. The register 2 value is now 4. Now the producer executes the counter is equal to register 1. The counter becomes a 6, and consumer executes counter is equal to register 2. The counter is equal to 4. Both the values are incorrect because the interleaved execution of these producer and consumer process, okay, which are sharing the common variable counter. So this kind of race condition may occur during the course of execution. Right. So now coming to the message passing. Process communicate with each other without resorting to shared variables. So the IPC facility provides two operations for this. One is called a send message and receive message. The message size may be fixed or variable. So if processes P and Q wish to communicate, they need to establish a communication link between them and then exchange the messages through send or receive primitives. What are all the implementation issues in this message passing mechanism? How the logical links can be established? Can a link be associated with more than two processes? How many links can there be between every pair of communicating processes? Only one link or two links? What is the capacity of a link? Is the size of message that the link can accommodate fixed or variable? Is a link is unidirectional or bidirectional? So the communication link is physical, means then it is shared memory or hardware bus or network. If it is a logical, means then it is a direct or indirect communication, synchronous or asynchronous communication, or automatic or explicit buffering. Processes must name each other explicitly in the direct communication mechanism. So send P message means send a message to process P. Receive Q message means receives a message from process Q. Properties of communication link. Direct communication is links are established automatically. A link is associated with exactly one pair of communicating processes. Between each pair of there exists exactly only one link. The link may be unidirectional, but it is usually a bidirectional link. Indirect communication. Messages are directed and received from mailboxes. So a mailboxes will be created between two sets of that is n number of processes. Each mailbox has a unique ID. Processes communicate only if they share a mailbox. Properties of this indirect communication is link established only if processes share a common mailbox. If it is only shared, only the link is established. A link may be associated with many processes. Each pair of processes may share several communication links. Link may be unidirectional or bidirectional. What are all the operations? Creating a new mailbox, sending and receive messages through mailbox, deleting a mailbox. So what are all the primitives associated with this? Send A message means sending a message to the mailbox A. Receive A message means receive a message from mailbox A. Now mailbox sharing. P1, P2, P3 are three processes which are sharing a mailbox A. P1 sends, P2 and P3 receive. So which P2 or P3 will get the message? The solution is allow a link to be associated with at most two processes, allow only one process at a time to execute a receive operation, allow the system to select arbitrarily the receiver, sender is notified who the receiver was. So these three kinds of solution can be provided for mailbox sharing type of indirect communication. Synchronization. Message passing model may either be blocking or non-blocking. Blocking is considered as synchronous. What is blocking? Send. The sender is blocked until the message is received by the receiver. Blocking receive. The receiver is blocked until a message is available. Non-blocking means it is considered as asynchronous. Non-blocking send. The sender sends the message and it continues. It does not wait. Non-blocking receive. The receiver receives a valid message or null message. This is another message passing example for the producer and consumer problem. Buffering. the queue of messages attached to the link. Okay, so this temporary storage will be associated with any communication link, that is called as buffer. These buffer can be implemented in one of the three ways: either zero capacity, no messages are queued on a link, sender must wait for the receiver. Render's first condition must be there, that is, once the sender receives, sender sends, the receiver should receive. The communication link between this sender and the receiver in the zero capacity has no storage capacity. Sender should send, receiver should receive, that's it. Bounded capacity, finite length of n messages, sender must wait if the link is full. There will be n number of storage. If that n number of storage capacity is full, then the sender should wait. Unbounded capacity, infinite length of the buffer, sender never waits. So this is about the IPC mechanism in the operating system. So thank you. We will continue in the next lecture.